Let's begin working on forces in 2 dimensions. So this is 2.4. Forces is section 2, is chapter 2, and we're in activity 4. So if you haven't done so, please read Coletta's book, chapters 4 and 5. And this will be related to homework 5, two-dimensional forces in sapling for physics 121, and homework 8, two-dimensional forces in physics 111. Let's go on to the next, go on to the problem. So we're actually going to do a problem in the lecture tutorials. So here we are in the lecture tutorial, which is the sub part of the activity. And just like the last activity, I want you to start off all lecture tutorials by typing in your name, okay, and your last name, and you'll go up here and save this right away in your desktop area, and that way you can turn it in later on in the next activity, which is an assignment. All right, so let's go ahead and begin this problem. So here we have a block that is being pulled up and to the right at a 30-degree angle by a string, and that person who's pulling it with the string is pulling it with 55 newtons of force. It's a 10-kilogram block, and the cord makes a 30-degree angle above the horizontal. There is kinetic friction working on this. It is moving, so therefore it does have kinetic friction working on it, and that coefficient of kinetic friction is 0.25. And so we are being tasked with trying to find out what the acceleration of the box is. So this is a lecture tutorial worksheet problem, and you'll notice that just like the name area, this is also a fillable area, and this is a fillable area, but where you draw your force diagrams, it is not. So we're going to have to actually use our shapes to actually create the force diagram. All right. So let's go ahead and begin creating the force diagram. So go ahead and start drawing your force diagram given this problem, and pause the video while you're doing it. All right, we're back. So what I'm going to do is I'm going to go into, again, I'm going to go into your comments area, and that's going to pop out this place. So I'm in Adobe Reader. I hit comment right here, and it's going to pop out, and these tools are going to now appear here in the secondary window. I'm going to go ahead and click on this arrow and push it back. So now I have a large area to work with. And again, the tools that I'm going to be using is the text box here, the pencil, eraser if I make a mistake, but most importantly is the drawing tools. In the drawing tools, I'll be using a lot of lines. All right, so let's go ahead and do our force diagram. What is physically touching this object, and what objects are interacting with this block? Well, the block has mass, so that means it's going to have the non-contact force due to the earth pulling down on it, so its weight, which is going to be the mass of the block times gravity. It's sitting on a surface, so that means there's going to be a normal force working up perpendicular to the surface. And it's also going to has friction, okay, and that is going to be parallel to the surface. That frictional force will be parallel to the surface and opposite the direction of the velocity. Okay, it's being pulled up and to the right by a string, so it's going to have a tension force working on it. So I'm going to go ahead and draw those now. All right. I'm going to go ahead and click on my shapes area. I'm going to draw the vector, and I'm going to begin by drawing the weight of the block. And I'm not sure about the size of these. I just want to make sure I draw the vectors correctly. So I drew the vector down, and I'm going to label this mg. Again, click off the text box, click back on it to make it smaller, and now I can move this into place. Oops, I forgot to draw the direction, or I forgot to type in the direction of that vector. It's pointed down in the negative y direction, so it's negative mg in this case. All right. The surface is creating two forces. It's creating a normal force, which is perpendicular to the surface, holding, so the surface is holding it up. And I'm going to label this normal force. So point it up, so it's positive, pointed in the y direction. Click off the text box, click back on it, make it smaller, move it into place. There we go. We got the normal force pointed up. And it's going to have a frictional force. Now, this object is moving to the right, so it's got a velocity vector to the right. I'm going to make this a little bit over here. So it's got a velocity vector to the right, which is pointed in the positive x direction. And I'm assuming it's probably going to be speeding up in that direction, but it is going to have an acceleration vector on it. So it didn't say, it didn't indicate if the problem, if it is speeding up or slowing down, but let's just go ahead and assume right now it is, just in case. So it's got a positive acceleration vector. It's going to have an acceleration vector on it. And I'm going to just make it for now pointed to the right in the positive x direction. All right. So when we learned about the types of contact forces, we learned that if there is kinetic friction, that vector is going to be opposite the velocity vector, right? It's a resistive force. Friction is a resistive force. So it's going to be opposing the velocity vector. Okay, it is a force. And we label this mu sub k. I'm just going to use a u sub k times the normal force. And that's pointed to the left in the negative x direction. And to sub the k, I'm going to go up here to my subscripts, make it sub. And now I'm going to squeeze down this and move it over into place. Right? We have a force due to we have a string attached to the object. Gonna not make this so big. And is pulling it up and to the right at a 30-degree angle. So I'm going to label this tension T. I'm not going to put a plus or a minus to that. I just want to, I'll put that when I break it up, due to due to the angle 30 degrees. So it's pointing up and to the right. And I'm going to actually go ahead and indicate the angle here in the text box. 30 degrees. Move it right there. Now this angle 30 degrees, it makes this it's making a triangle right here. This arrow is pointing up and to the right. So I'm going to go ahead and draw a vector. So I need vectors beginning here. I'm going to make a triangle. Pointing to the right. So it's making a triangle pointing to the right and up. It's a little bit hard to make vectors here. It's easier for me to make them off to the side and then draw them there. Okay, so here's my triangle. This arrow is pointing up to the right. That means the vector addition is going to be to the right and then up. Add those two together, and then the displacement vector or the magnitude vector is pointing up and to the right. All right. Now I'm going to label those. A lot of people don't like to label the trigonometry in there. I like to have all the information available in my free body diagrams. So I'm going to do the horizontal arrow first. Okay, so this side is adjacent to the angle 30 degrees. Okay, and this the t vector that's up and to the right is a hypotenuse. So that'll be the hypotenuse cosine of 30 degrees. It's cosine because it's adjacent to it, and it's going in the positive x direction. So that's why it's positive t cosine 30 degrees. All right, let's go ahead and draw the upward angle right now. So this side is opposite the angle 30 degrees, so it's going to be the hypotenuse sine of 30 degrees, and it's pointed up. So positive t sine of 30 degrees. I'm going to move that into place. So here's your force diagram. Here's what it looks like. Right? Now what I want you to do is take our force diagram that we drew, and I want you to transfer it into addition of vectors using Newton's second law here, and go ahead and type out those. This is a typable area, so you could actually fill this out. So let's go ahead and do that now, and let's see what you get. So please pause the video now. All right, here we go. So I'm going to start with the sum of forces in the x direction. So I'm only going to look at horizontal vectors. I have two. I see one t cosine of 30 degrees pointed to the right is positive. I see a leftward pointed vector that's negative mu sub k times the normal force. So I'm actually going to start with the left arrow. So call that negative mu sub k times the normal force. Let me see if there's a way to subscript this. So I'm not sure if there's a way to actually subscript this in the actual text box. So we're not going to do that. We're going to call just UK as the coefficient of kinetic friction. So we've got our negative mu k times normal force, space, plus, now we're going to add our plus t cosine of theta, t cosine of 30 degrees. And we're going to set that equal to mass times acceleration in the x direction. Okay? We're assuming there's going to be some type of acceleration in the x direction. I don't know if it's pointed to the right or left. I'm assuming it's going to be speeding up while being pulled to the right, but something weird may happen. I'm not sure. All right, let's move on to the sum of forces in the y direction. We've accounted for both of our horizontal forces. We have, it looks like 1, the normal force, 2, t sine of theta, and 3, negative mg forces in the y direction. So I'm going to start off with a normal force. Got a positive normal force, space, plus, I'm going to do the t sine of 30 degrees, space, negative mg, and I'm going to set that equal to space, mass times acceleration in the y direction. But since it's not accelerating up or down in the y direction, we're going to go ahead and set that equal to 0 newtons. Got to make sure we put the units on it. Okay. So now I have an equation for the y direction, and we could use that later on when we figure out what the acceleration is in the x direction. So go ahead right now, and I want you to find out what the acceleration is in the x direction. That would be this part right here. That's this vector. The acceleration in the x direction. Now you're going to have to merge these two equations together. We know what t is, but we do not know what the normal force is. So typically if you have friction, you're going to use the y direction forces to solve for the normal force, and then substitute that in for the normal force here, and then solve for the acceleration in the x direction. So please do that now. So you could do this really quickly in the actual Adobe file. So I'm going to give this a couple spaces. All right. Since this whole area is equal to 0, so we got the normal force plus t sine of 30 degrees minus mg is going to be equal to 0. Okay? And now we have to solve this for the normal force, because eventually we're going to put that in here. So I need to bring t sine of 30 degrees onto the other side, and I need to bring mg onto the other side. So I'm going to subtract t sine of 30 degrees from both sides. And that will give me the normal force minus mg equals negative t sine of 30 degrees. I don't know why I keep hitting the M button. Okay, and so now we need to add mg to both sides. So we're going to do that now. Going to add mg to both sides. And so on the left side, we'll just have the normal force left over. Then we'll have our mg minus t sine of 30 degrees. And that is what our normal force is equal to. So now go ahead and substitute that into right here for this normal force. So when I do that, what I'm going to do, suppose I should have given this a little bit of room so it looks cleaner. So if I do that, I have negative mu sub k, and that now I'm going to put in the normal force, which is mg minus t sine of 30 degrees. So that is our normal force. And then I'm going to add in t cosine of 30 degrees. And that's equal to the mass times the acceleration in the x direction. Okay. And now we have mass times acceleration in the x direction. I'm going to divide mass by both sides to get acceleration alone. So I'm going to just copy this equation right here, paste it right here. I'm now going to divide both sides by m. When I do that, I'm going to divide this whole thing by m. Divide by m. And then I need to divide this by m. And now go ahead and put in, so this entire expression is divided by m, and this entire expression is divided by m. And now we have a by itself. So go ahead and put in the actual numbers and solve for this acceleration. All right. Thank you. Thank you for listening to this. What I want you to do is I want you to go through the this video, but also the sub videos, the support videos that I put on there. And it has additional videos to help you out, and other instructors and how they've done things. So I want you to complete this this entire tutorial. So you've got the second problem where you have a block being pushed across a surface, and it has a coefficient of kinetic friction, so there's going to be friction. It is probably going to be speeding up to the right. I don't know. It depends on what the sign of the acceleration vector is. You have another block that is being pushed up and to the right by a 10 Newton force, there is a frictional force on the wall. Okay, again, you have to solve for the acceleration. I'm not sure if it is speeding up as it's moving up, or if it's slowing down as it's moving up. Or it could be even speeding up as it's falling down. This may not be enough force to hold up this block. And then finally, we have this problem where you have a rope. You have two ropes holding up a box in static, and you're supposed to find the tension on rope on each of the ropes that supports it. Okay, so just go ahead and put one rope. So you'll write your answer in. If, let's say, one rope is 5 newtons, you'll go 5 newtons. Oops, 5 newtons, and then comma, and the other rope, let's say rope 2 was 3 newtons. Okay, so you'll do that there. All right, good luck. Hope you get through. If you have any questions, please attend the virtual office hours. Bye.